Hello students, welcome to the next lecture in ATS533. This next lecture is about two chapters actually from the IPCC Fifth Assessment report, chapters 3 and 4, which are about the oceans and the cryosphere. Now everything that we saw so far in the class had been about the atmosphere, and actually right here at the very beginning of this lecture I do want to turn back to atmospheric things just to finish up one topic that we saw earlier, and that was weather patterns. This would in many ways be one of the most important impacts we could find out about global warming. It would be extremely important if we could find out, for example, that thunderstorms and tornadoes were happening in a different part of the world due to global warming, or that snowstorms are happening in a different part of the world due to global warming, or that El Nino was more common due to global warming, or that El Nino was stronger, or hurricanes or something like that. This would in many ways be the most important result, but it's also in many ways the trickiest result to come up with regard to global warming, because remember, individual weather events don't really count as evidence. It's only in the sense of like the frequency of these things and so on. So for example, it would be really interesting if we could say, for example, that there were clear patterns in regard to the pressure at the surface of the Earth. Now, survivors of like a physical meteorology class would already know that in fact pressure is a conserved property, in the sense that like added over the whole surface of the Earth, or averaged over the whole surface of the Earth, it works either way, the total pressure has to be the same no matter what weather patterns are going on, but that doesn't mean it has to be the same every place. And so we could actually have a situation where like there was more low pressure systems in some location, and that could mean that like it's stormier in one location as due to global warming or whatever. Now, that being said, that's proven to be difficult to show. The IPCC reports that it does seem that pressure has decreased across the tropical Atlantic and over large regions of the Pacific and the South Atlantic, but it does not seem like that's a very convincing That might be related, for example, to hurricane development. It's beyond the scope of this class. Please take tropical meteorology if you want to know about how, like, in general, pressure being lower across the Caribbean and the tropical Atlantic in general contributes to more tropical cyclogenesis, that is to say, more formation of hurricanes, but that's a very broad connection, okay? This is certainly not very strong evidence that, like, therefore there should be vastly more hurricanes, the way there frankly have been vastly more hurricanes. Same with, like, it would be really interesting and important if there were connections between global warming and the wind speed at the surface. I mean, it would be really interesting to have a hypothesis that would say a warming world is also a windier world, or a less windy world, both of which would have interesting implications for, say, wind power generation, or evaporation rate, or whatever. But we don't even have a good hypothesis about that yet. And as the IPCC reports, in summary, confidence is low in the changes in surface wind speed over land and over the ocean due to remaining uncertainties in data sets and the measures used. There are some studies that say that there might be regional differences, but nothing consistent. This is certainly something for which we don't really have any confidence about yet. It would even be more interesting if it could turn out that there was a connection between global warming and wind speeds aloft, like wind speeds in the jet stream. That could have all kinds of interesting meteorological consequences, in the sense that, like, it would be changing cyclogenesis patterns in the atmosphere as to where troughs and ridges and cyclones and anticyclones form, which could have very major impacts for, like, the people who live in certain areas in terms of the amount of precipitation they got or whatever. But we actually don't really have any confidence in this yet, because it's frankly not even been studied all that much. Remember, the IPCC is trying to talk to policymakers and stakeholders and tell them the state of the research, and the truth of the matter is the state of the research is not so great when it comes to observations of winds aloft. We only measure the winds aloft using weather balloons with packages of instruments behind them, and we only do that twice a day. And we only do that a handful of it's like 100 locations across the United States, a few hundred locations around the world. There just isn't enough data. We couldn't really make this kind of research work. Now, one possibility where we do see a change with regard to how the circulation of the atmosphere is changing with regard to global warming is something we saw a hint about in the previous lecture. It might be the case that there's something going on with regard to the Hadley circulation. Remember the Hadley circulation? I'm trying to think. Yeah, I do have a slide about that again, just to refresh you. Where we have rising motion at the equator, upper level divergence, air sinks around 30 degrees north and 30 degrees south and returns to the equator. It's one of the broad circulation cells in the atmosphere, and there's two of them there. And in general, it's found that there does seem to be some trend in the strength of the Hadley circulation, also in the Walker circulation. The Walker circulation is a similar sort of idea, except instead of being in the north-south direction, it's in the east-west direction. By all means, please take Tropical Meteorology ATS533, which is an elective in the environmental science curriculum. I would love to tell you all about Hadley cells and Walker cells and why they're important and how they change and so on. But there does seem to be some shifts in these patterns. In particular, in the context of climate, one of the terms we talk about is the width of the tropics. This is like as in the distance between the sinking branch of the northern Hadley cell and the sinking branch of the southern Hadley cell. This is the width of the tropical region, like the distance between the subtropical highs in the northern hemisphere and the subtropical highs in the southern hemisphere. It turns out there's actually lots of different ways to define the width of the tropics. But in this diagram here, what we're seeing is about 30 years of measures of the width of the tropics. And you can see, like one definition of the width of the tropics is these blue definitions. Another one is the red ones. Another definition is the orange ones. Another definition is the green ones. So these are all, and then within the blue ones, say there's several different studies that have tried to come up with a width of the tropics for each of those years. But if you actually kind of look through it here, there does seem to be some evidence of that there's a positive trend in most of these data sets over the last 30 years. It does seem like the tropics are expanding. So that pushes other weather patterns farther to the north, like the subtropical highs. Well, the subtropical highs tend to be located over deserts, so pushing the subtropical highs farther to the north might lead to desertification, that is to say the expansion of the deserts, or the shifting poleward of the deserts. This is a potentially very serious, this is an interesting possibility that maybe we are changing the width of the Hadley cells, which is effectively widening the tropics and pushing all the rest of the weather farther towards the poles. An example of a possible consequence of that is a change in the storm track. Now, we're not going to get bogged down into how you define the storm track, but this is an actual defined quantity in meteorology that is related to how often cyclones pass a location. And you can actually come up with a quantifiable way of describing how often or what is the paths that cyclones tend to take at a given time of year or in a certain part of the world or whatever. And there is some evidence that there is a poleward shift in the storm tracks. Cyclones are generally tracking farther to the north than farther poleward of the northern hemisphere, that would be to the north, and farther to the south in the southern hemisphere. So, and as it says here, there is evidence for a poleward shift of storm tracks and the jet streams since the 1970s. Based on these consistency of these trends and how that agrees with the observed widening of the tropical belt, there seems to be, it is likely that the circulation features have moved poleward since the 1970s. But methodological differences between the studies means that there is actually low confidence in characterizing the global change in this in terms of blocking. Blocking is another meteorological piece of jargon that has to do with to what extent the weather patterns kind of get stuck. Like we get stuck under a high pressure system, and instead of it moving on in a migratory way, it is blocked, or we get stuck under a cyclone or something like that. They're saying there's not really any changes in blocking, but there do seem to be a poleward shift in the storm tracks. Really, one of the holy grails of this kind of research would be to know if there's some changes in El Nino. Now, when we start talking about paleoclimate in the next lecture, there's a whole subdiscipline called Paleo El Nino, where they're actually studying El Nino of the past and trying to figure out over the last 1,000 years, over the last 5,000 years, over the last 5 million years, have there been changes as to how often that weather pattern known as El Nino happens. This is not the class to learn about El Nino. If you want to know all about El Nino, I sound like a broken record, but take my tropical meteorology class as an elective within the environmental science curriculum. We spend weeks on what is El Nino and how it changes global weather patterns and how long it lasts. But I think you have a broad idea that El Nino is a weather phenomenon that happens every few years. It affects weather patterns worldwide. You get unusual weather, unusual distributions of tornadoes and precipitation and hurricanes and so on. And it happens every few years. There are some statistically significant ways to think that maybe we are going to be seeing more El Ninos in a warmer world. And that does see, again, don't worry about, like, the chart is more here to help me remember what's all going on here. But there is some reason to think that maybe El Nino is becoming less common, and maybe there is some reason to think it could be more common. And in fact, if you look at the diagrams here, most of these trends are not statistically significant. There is some reason to think, though, that there could be changes, but like I said, theory doesn't even help us yet know whether we would expect there to be more or less. The period over which we have good records is not that long compared to, well, I'll take it back. There aren't that many El Nino events that have happened since the Industrial Revolution, okay? They happen about every 4 or 5 years. We don't have a large enough sample, really, to make a very good connection about this yet. But that is definitely something that climatologists and atmospheric scientists would really want to know, because the global impacts of an effect like El Nino are very large. If they are happening more often or less often, that will make an important difference for environment, for economics, etc. Alright, so let's turn now to start talking about the oceans rather than the atmosphere. Now, I wrote here, unsurprisingly, much of the heat that is trapped by the greenhouse effect ends up in the oceans, but the unsurprising there might be less obvious than I had realized. Keep in mind, the ocean is a huge heat sink, okay? Because of its high specific heat capacity and so on. If the air is warmer than the ocean, the heat just ends up in the ocean. I mean, it just takes the heat out by conduction into the big heat sink that is the ocean. Plus, there's all this radiative transfer stuff going on, where we'll be learning more about in the second module. But I think you know enough from like ATS113 to know about like long wave up and long wave down and short wave up and short wave down. Well, greenhouse gases are increasing the amount of long wave coming down from the atmosphere, and well, 70% of the time that's going to be hitting ocean surface rather than atmosphere surface, and therefore, ground surface. So again, the heat is ending up in the ocean. But we'll learn more about the mechanisms of that in the second module. Now, just to be clear here, the book is actually talking about the bulk of the ocean, not the surface. The surface is literally like the top millimeter or so. I mean, and that often is what we're measuring the temperature of, but the heat is actually being stored in a layer of the ocean, potentially a few hundred meters thick. It's certainly not the deep ocean. I mean, we're not worried yet about changing the temperatures of, like, you know, the ocean at kilometers down, but we're certainly talking about a thick layer near the surface of the ocean. And, well, here's a picture I happen to have pulled off, I forget what website here, but this is showing the total amount of heat being stored in the Earth's ocean. There's some reasons why heat stored is a better measure than like average sea surface temperature increase. And you can see that over the course of the last 55 years or something like that, the total heat being stored in the Earth's ocean is increasing dramatically. Wow. I mean, that's quite a trend. There's not much ambiguity there about the trend here. And let's be clear, this is about observations. We're not yet talking about like ocean models or theory or anything like that. This is purely based, those calculations are purely based on instruments. I mean, I've talked before about the fact that we have all these buoys out over the ocean that gather meteorological and oceanographic data. Many of them are moored buoys where they have a long chain down to a big heavy weight at the bottom of the ocean, and there's instrumentation at various depths along the way that is measuring the temperature and salinity and ocean currents and things like that. There's actually all kinds of cool technologies that are used to monitor the temperature of the ocean below the surface. I can't remember what the name of this particular technology is, but you deploy these sort of little cylinders. I don't know, they're bigger than a paper towel roll, but they're not that big, all that big. And they, you know, by pumping in and out air, they first lower and then rise. and they report back to the satellite what the ocean temperatures they've seen, and then they sink back down to a depth again. I can't remember what that technology is called. All of those technologies, of course, are difficult to maintain because they're far from people. They're difficult to keep calibrated and so on. But we do. We go to enormous expense to go out there with research vessels from the National Oceanographic and Atmospheric Administration and actually go out there and maintain them. This picture, I love this picture. This is my actual college roommate, Patrick Ahern, who is actually the very first environmental science major from Creighton University back in the early 90s, and he has a job where, well, actually he has a different job now, but he used to go out to sea, on vessels that just went from buoy to buoy, servicing them. I don't know why he's laying out there on the buoy here, but whatever, that's not his service of buoy. Now, perhaps unsurprisingly, the warming of the Earth's oceans is not uniform. In fact, we can look at these trends here, and we can see that, well, let's see, if red means that there's a positive trend and blue means that there's a negative trend in the ocean temperature, well, it perhaps is not surprising that most places are relatively small but positive changes, although there certainly are some very large changes in the ocean temperatures in the northern subtropics across the North Atlantic and parts of the North Pacific. Just to give you a sense here, those trends are in degrees Celsius per decade, so like a trend of, let's just say, 0.2 degrees Celsius per decade, that's 2 degrees Celsius per century. That is a lot of warming. Think of the large amount of heat that it involves to change the temperature of the ocean by 2 degrees. I mean, even in classes like ATSEVS533, you learned that it takes 1 calorie of heat to change the temperature of 1 gram of water 1 degree Celsius. Well, a gram of water is just a tiny little squirt of water. This is the ocean we're talking about. The amount of heat that's involved is huge. And keep in mind, we're not talking just the very, very surface of the ocean. We're talking a thick layer of the ocean. In the context of climate, they usually characterize it as the top 700 meters of the ocean is being warmed by these processes here. And that warming is obviously important in and of itself, in the sense of it changes the habitat in which various creatures are living in the ocean. I mean, they may reproduce more or less effectively based on the ocean temperature, or the things that they eat may live more or less effectively depending, may be more or less abundant depending on the temperature. So the temperature of the water itself is in and of itself a problem, but one of the things that's most directly important for human experience is how changes in the ocean temperature are affecting sea level change. Now, sea level change, of course, is one of the, shall we say, sexiest things about climate change. Everybody has this idea about how sea levels are rising due to global warming. Even the general public, I think, has a broad sense that this is happening, although how much and why, they largely have misconceptions about. Let me help you sort out if you have any misconceptions about that. Basically, there are two main things that are happening associated with global warming that are both increasing sea level. One of them has to do with the melting of grounded ice. When I say grounded ice, I'm talking about ice that is above sea level. The stereotypical example would be like a glacier. Okay? When this glacier in this picture here melts, that water goes down rivers and streams and ends up in the ocean and increases the height of the ocean. This happens all the time in the natural world. I mean, humans are not responsible for the end of the last ice age. During the peak of the last ice age, sea levels were, something on the order of many tens of meters lower than they are now because so much ice was on the continents. Whereas when it melted, sea levels rose. So the right word for that is, the jargon for that is that it's grounded ice, ice that is above sea level. But you'd be surprised how much of the actual resulting sea level change is actually due to the thermal expansion of water. When water heats up, like most materials, it expands. Now, we don't normally think about this in our day-to-day lives because, frankly, the thermal expansion of water is relatively small. But that's because, in our experience, the amount of water we're talking about tends to be a small volume of water. So when it expands a small amount, you can't really see the difference. Oceans are huge, and they have no place to expand but up. Let me give you an example here. See, I've got a coffee cup here. Let's say we had 7 centimeters of water in that cup. If I heat that cup of water a whopping 50 degrees Celsius, I did the math on a spreadsheet, and it turns out the water will expand about 1%. So that would be about 0.07 centimeters. That's less than 1 millimeter higher. So I warmed up my cup of coffee up in the microwave, and it just barely made the water. I'm not going to even notice that. And that was a huge warming, 50 degrees. But let's do the same sort of thing for the top 700 meters of the ocean surface. If I take 700 meters of the ocean surface and I only warm it up, not 50 degrees Celsius, how about 1/10 of 1 degree Celsius? If I warm it up 1/10 of 1 degree Celsius, I get an expansion of, oh my goodness, it's not that much, 207%. Well, that hardly sounds like anything. But for a 700 meter thick layer, that actually adds up to expansion of 1.5 centimeters. The ocean is physically 1.5 centimeters higher because I added enough heat to make its temperature increase by a mere 0.1 degrees Celsius. So now this all scales linearly, so if I said I was going to change it by 1 degree Celsius, that would be a 15 centimeter change in the height of the ocean. Oh, and some places the rate of change was fast, more than like 1 degree Celsius per century. There were places as high as 3 degrees Celsius. That would be a 45 centimeter increase in the height of the... Oh, it really adds up. And yes, it does. And in fact, the observations bear that out. Now, we'll talk about where these observations come from in just a moment, but we have good in situ observations of the height of the ocean all the way back to the 1870s. Again, this is globally averaged. Now, I say globally averaged because you might be surprised to find out, but the ocean is not perfectly flat. Parts of the ocean are physically higher than other parts of the ocean. In fact, that's part of El Nino, is rearranging the areas of the higher and lower sea surface height. But the range from the places where the sea surface is highest to the places where the sea surface is lowest is only on the order of 10 centimeters to a half meter or something like that. It's not huge, but sailing from one part of the ocean to another part of the ocean can be uphill. Admittedly, a very gentle uphill. You're only climbing a matter of centimeters as you go kilometers down, away. But the surface of the ocean is not leveled. That's why we have to worry about an average sea surface height. But if we had a change in if we define the average sea surface height around the world as 0 on this diagram here, we would see that over the last 140 years or something like that, observations are showing that globally average sea surface heights have increased by about 10 inches. What is 10 inches? I don't know. Is that about 25 centimeters, something like that? So we have a real expansion of the ocean. And by the way, you can see there's a range of different estimates. That's why there's error bars on there. And you can see, by the way, there is a satellite observation starting in about the mid-1990s that confirms the rate of expansion quite well. How we actually do this has to do with tidal gauges. Harbors have tidal gauges that measure how high the sea surface is due to tides. Tides are extremely important for the ships that are coming into the harbor. They need to know how high the sea surface height is. And so we routinely measure this at all harbors, but then that information we can work with it to process climate information out of it. Like how, yes, you had high tides and low tides and all that, but when you average it out, how much has the average height of the ocean changed? And again, they have to be careful about things like ocean, like inhomogeneities as we've moved tidal gauges and all that kind of stuff. But again, that's all documented. And as long as you know about inhomogeneities, you can fix them. We also do this using remote sensing techniques from space. There are radar altimetry methods where a satellite in orbit actually uses a radar beam to map the height of the ocean surface. Now, in practice, we actually do that. We have a number of different satellites. There's Jason 3 was recently launched that can measure this sort of stuff. This is often used. There's actually a whole subdiscipline of oceanography called synoptic oceanography, where they are mapping these areas of high sea surface height and low sea surface height, which kind of work a little bit like cyclones and anticyclones in terms of the currents and so on. That's beyond the scope of this class, but we actually routinely map the height of the surface of the ocean to literally millimeter accuracies using satellites. And so we have a satellite, an independent source of information, namely the satellite archive, that confirms what the in situ observations from tidal stations are saying about the height of the ocean. Now, I mentioned then that there were two factors that were increasing the height of the surface of the ocean, namely the melting of grounded ice and the thermal expansion of the ocean. What you might be surprised to know is that the melting of sea ice doesn't matter. Ice that is actually on the surface of the ocean, whether like an iceberg or like, just flat like the surface of the ocean is frozen, doesn't actually change the volume of the ocean very much, because that's water that's already displacing other water, right? When the iceberg melts, the volume of the ocean is still about the same. It's in the same sort of way that if you fill a cup of water with water and ice, when the ice melts, the cup doesn't overflow, right? So in that way, sea ice doesn't matter. I mean, don't get me wrong, there's important reasons why melting of sea ice does matter, but it's not about sea level change. So, okay, you don't have to look very hard to find images, websites, movies, whatever, where you see stuff like this, where like a city is inundated due to global warming, and it looks like Venice or something like that, but it's just, yeah, but this is all fake, right? I mean, the real changes in the height of the ocean surface have been more on the order of like 25 centimeters. Does that matter? I mean, 25 centimeters, we don't mean that, by the way, that the water is 25 centimeters farther up the beach. We mean it's 25 centimeters higher. Depending on the slope of the beach, that could be a long ways further inland. But does that matter? Okay, well, that is actually kind of an interesting question. Nobody's going to drown because of that. On the other hand, I found some good statistics that show that about 10% of the world's population lives quite close to sea level, let's say within 30 feet of sea level. Now, the ocean is not going to rise 30 feet anytime in the next, well, I mean, barring like, the collapse of the Antarctic ice sheet or something like that, we're not going to have 30 feet of sea level change. But what I'm saying here is that there are reasons why the rise of the sea level is important, because it increases the risk of damage during storm surges and prolonged flooding and so on. Like for example, when a hurricane comes ashore, there is the storm surge where, because of the mechanics of how the winds and the pressure in the hurricane interact with the ocean surface, the ocean is physically higher than it would otherwise be. That's why you get the flooding of that salt water that comes inland during a hurricane. But under the impact of global warming, that's an additional 25 centimeters or something like that of water that is coming inland. That's that much more damage of things that should have been high enough to not be damaged. Plus, that's just that much more strain on the infrastructure of cities. I mean, New York City subway system is already below sea level. It is a Herculean task every day to keep the New York City subway system from filling with water. There are pumping stations and so on, because while it's all built in tunnels that are lined with concrete and stuff like that, it all leaks. There's a constant system of pumps that pulls water out of there. All of that would just be under that much more strain with 25 centimeters more water to be putting pressure on the system, creating more reasons why the system could flood. And the subway system, oh my, but how about the foundations of buildings, or the tunnels that the electrical and the water and the internet and so on all move through? That's all at or below sea level in these kind of coastal cities. It's a constant effort to keep that stuff dry now. If we keep adding more and more water, it gets easier and easier for things to go wrong, and we lose this infrastructure. Another good example would be what happened in Hurricane Katrina in New Orleans. The lower Ninth Ward is slightly below sea level, and it was kept dry by a system of levees and pumping stations that, when that system failed, the lower Ninth Ward filled with water. Okay? Another 25 centimeters of water of sea surface height would have made it that much more difficult to keep the lower Ninth Ward dry, and that much easier for a storm system to come through and cause the failure of the systems and flood the lower Ninth Ward. We're going to see that problem all around the world. Most of the great big cities of the world, Tokyo and whatever, name them, I'm drawing a blank. They're coastal cities. Their infrastructure is right at or slightly below sea level. We are going to have this problem as sea level changes. Now, before we go on and talk about the cryosphere, I want to just ask you a couple quick questions. Question one. As the planet warms, observations show that the storm track is shifting A, poleward, B, equatorward, or C, there's no evidence that the storm track is shifting. What did we learn towards the beginning of this class about how the storm track was changing? Make a choice from those three options and get a little feedback before you move on to question 2.